So now we move on to parallel resonant bandpass filters. I hope you're getting the feel here that all of this stuff is fairly repetitious. We solve them generally the same ways. There may be some things that are drawn out that you've learned previously that hopefully you still have in your bag of tricks from previous lessons and from previous courses. So the parallel resonant bandpass filter is a type of filter using a parallel resonant circuit as shown in the diagram. So you can see we've got that little LC parallel circuit. It kind of looks like a tank like we've seen before. Recall that a parallel resonant circuit has maximum impedance at resonance. The circuit in the figure acts again as a voltage divider. At resonance, the impedance of the tank circuit is much greater than the resistance. Thus, most of the input voltage across the tank produces a maximum output voltage at resonant or the center frequency. For frequencies above and below resonance, the tank circuit impedance drops off and more of the input voltage is across the resistor R. As a result, the output voltage across the tank circuit drops off, creating the band pass characteristic. So if we look at this little example down here, we've got a circuit. We want to calculate the center frequency. So what we do is use the relationship, the 1 over 2 pi LC that we've already seen. So the center frequency is 1 over 2 pi, the square root of 10 microhenries, 100 picofarads. We get 5.03 megahertz. Determine the center frequency and bandwidth for the bandpass filter if the inductor has a winding resistance of 15 ohms. Okay, so they're introducing a winding resistance. We've got a resistor of 82 ohms. The tank circuit forms the LC 50 millihenries, 0.01 tens, hundredth of a microfarad. Recall that Chapter 17 that the resonant center frequency is a non-ideal tank circuit. So the non-ideal case, we have to include the winding resistance. So you can see the winding resistance in there in the non-ideal case. So as we enter the values in here as given and as given in the stem of the problem, there's our 15 ohms for the winding resistance. The rest are from the circuit. We get a center frequency of 7.12 kilohertz. Again, I encourage you, pull out your calculator, work through this. Do the denominator first. Actually do what's under the square root first, then multiply by 2 pi, invert that, and multiply by what's under the square root here. So the Q of the coil then at resonance, there's our relationship for Q, X sub L over the winding resistance. X sub L then 2 pi FL gives us a value then of 149. Again, notice no units. It's a measure of a frequency, a figure of merit. The bandwidth of the filter then is that center frequency by the Q. So now that we have Q, we have our center frequency from the two previous calculations. The bandwidth is 47.8 hertz. Not very wide if you think about it. You know, a lot of times we get a bandwidth in the thousands, the kHz range. This one is a very narrow 47.2. So we've got a very narrow bandwidth here that we're looking at. Note that since Q is greater than 10, so what's Q? In this case, it's 149. The simpler formula, center frequency equal to 1 over 2 pi LC, could have been used to calculate. Try it and see. Pull out your calculator, work through, find out what the minuscule difference was between solving for the center frequency using the simple formula versus using the non-ideal. Band stop filter, the next one, the band stop filter is essentially the opposing a band pass filter in terms of responses. The band stop filter allows all frequencies to pass except those lying within a certain stop band. So we've got a notch here that we're looking at. There it is. So there's the notch response. There's our center frequency. Here are our points, FC1, FC2, our critical frequencies that form the points for the bandwidth. Again, we can see that's at that 70%. 0.707 times Vmax, which we also call the minus 3 dB point. Okay, so get used to this. In your 111 course, you also learned this was called the half power point. So a band stop filter can be formed from a low pass and a high pass as shown. So now we're taking a low pass and a high pass and sticking them together in such a way that we build that notch out of both sides of the response that's going on, the low pass response and the high pass response. If the low pass critical frequency FC1 is set lower than the high pass critical frequency FC high, okay, low and high, a band stop characteristic is then formed. So you can see we've got a little bit of an overlap there, and we've got a band stop being indicated. A series resonant band stop filter then is used in a band stop configuration. Basically, it works as follows. At resonant frequency, the impedance is minimum, and therefore the output voltage is minimum. Most of the input voltage is dropped across the resistor. At frequencies above and below resonance, the impedance increases, causing more voltage across the output. Look at an example here. Find the output voltage magnitude at F naught and the bandwidth. Okay, so if you take a look at what's given here, 56 ohms, a winding resistance for the inductor at 2 ohms, 100 millihenries, 0.01 microfarads. Okay, work through this example. Okay, it's fairly simple. It follows just exactly what we've seen before. Pull out your calculator, work through it, write it down, become familiar with the flow here. You know, we've got our voltage divider, we've got our solution for the center frequency, we've got our solution for Q. From Q and the center frequency, we're able to solve for the bandwidth. Okay, mark this down in your notebook and keep track of it along with the formulas. The parallel resonant band stop filter, again, a band stop configuration shown here where we've got a capacitor and inductor then in the series part of the circuit, okay, with the output taken across the resistor. Okay, at the resonant frequency, the tank impedance is maximum, and so most of the input voltage appears across it. Very little voltage is across the R at resonance. As the tank impedance decreases above and below resonance, the output voltage increases. So again, another example here from your text. You know, the same type of example. Work through it and use each of these relationships. Again, voltage divider, center frequency, Q, using what you've calculated. Find the bandwidth from the Q and the center frequency. In this case, a very narrow 92 hertz. Parallel band stop filter, again, another one, a little more sophisticated here. They're showing it where we have a winding resistance here. So they want us to use the non-ideal case. You can see right here in the solution, there's our winding resistance being placed in the relationship. Notice it's an 8 ohm winding resistance. Again, very small. Go through and do it this way. Go through and do it with the 1 over 2 pi over the square root of LC and see what difference you come up with for the center frequency. Okay, because it's very small, you can probably get away without using the sophisticated one. But prove it to yourself. Okay, so we've got then they want us to draw the output response curve. There's our output response curve based upon our calculations. So that is all of passive filters. As you've seen, it includes a lot of the things that we've already seen. We're just putting them to use differently. So make sure you practice these. You pull these up, pull these examples out, write them down, work them out. They're going to benefit you later as we proceed through the course and as you proceed through your education and your career.